welcome Florian. He's a fifth-year PhD student from Stanford University. His advisor is Dan Bonnet. So probably many or most of you should know Dan and his group. And probably you have already seen a few papers from Florian because he's working in a very interesting field. It's the intersection of computer security, machine learning, and also cryptography. And in today's talk, he will focus on machine learning and security. And as far as I know, we will hear about some of the latest results in that area. On the one hand, he talks about adversarial examples, or in general, adversarial setting for ML algorithms. And then the second part will cover privacy. So how can we enhance privacy in such a setting? And I'm really happy that you give a talk today and looking forward to the presentation. So welcome.
Thanks a lot for the very nice introduction. Okay, so let's get started. So yeah, hi everyone. As Torsten said, I'm a fifth-year PhD student at Stanford University, and today I'll be telling you how to measure and enhance the security of your machine learning models. So we've made tremendous progress in machine learning over the past decade, and this has enabled a plethora of new exciting applications. For example, our phones can now recognize objects that surround us. We've achieved superhuman performance at challenging games like Go, and we can seamlessly translate between hundreds of languages. These applications typically aren't perfect. They fail occasionally, but without causing much harm to users. So an image recognition model might mistake one object for another, say a computer mouse for a shoe, or a game playing agent might fail in unexpected situations like this penalty shooter that can't score when the goalkeeper is lying on the floor. And model failures also aren't limited to making wrong decisions. They can be about unintentional data leakage as well. For example, about 2 years ago, a user noticed that when translating from Somali to English, Google Translate would sometimes spit out memorized biblical verses from its training set. But not all machine learning failures are this benign. So as we start to use machine learning in a broader range of applications, mistakes can have much more dramatic consequences. So one example here is obviously self-driving, where a single mistake from a machine learning model can result in an accident and in human death, and this has happened in the past. The situation can be even more challenging when machine learning models are made to interact with explicitly malicious users. So you might recall Microsoft's chatbot, Tay, that was deployed on Twitter and started spouting racist and misogynistic slurs after 24 hours of interactions with users. And data leaks can also have much more serious consequences than our previous Google Translate example, when the leaked data is private information from users. A recent work of mine was actually the first to show that production-grade machine learning models can leak personal information contained in their training data, such as phone numbers. So these dramatic failure modes of machine learning call for research that helps us to better understand and to improve the worst-case behavior of these models. So my approach, which is inspired by my background in computer security and cryptography, is to study worst-case behaviors by considering the presence of an explicit adversary that aims to undermine the machine learning system. The goal here is twofold. On the one hand, some machine learning models will be deployed in the presence of explicit adversaries, like Microsoft's chatbot, and we want to guarantee the security of these systems. Now, on the other hand, understanding and improving machine learning's behavior against worst-case adversaries can also give us insights for generally making machine learning better and more trustworthy. And so my work on adversarial machine learning has made contributions generally to our understanding of machine learning security, how to measure it, and how to enhance it. My research in this area is mainly focused on three main thrusts. Part of my work has been foundational on identifying new threats to machine learning systems and characterizing the adversaries that we want to protect our models against. So, for example, I introduced model stealing attacks where a user abuses access to a prediction interface to reverse engineer proprietary models. And this is now recognized industry-wide as one of the main threats to deployed AI systems. I've also done foundational work on modeling the threats of evasion attacks, or so-called adversarial examples, where an adversary tampers with a model's inputs to cause the model to fail. A second part of my work is focused on designing machine learning systems that aim to defend against these adversaries, where I've proposed new defenses to make machine learning both more robust against evasion and more private. And finally, I've shown how to improve the way in which we evaluate such defenses, mainly by building stronger attacks that demonstrate that many proposed defenses aren't actually as effective as initially claimed. My work here has directly impacted the design of some systems such as AdBlock Plus, a web-based ad blocker you might be using, which has over 100 million active users. And so in this talk, I'm going to be focusing on 3 representative directions taken in my work over the past few years. So I'm first going to talk about my work on evading machine learning models, and then I'll give an overview of my research on improving the privacy of machine learning systems. So let's first talk about evading machine learning models with adversarial inputs. So we typically refer to adversarial inputs as adversarial examples. So what are these? So consider this image here on the left. We all agree this is a cat, and a modern image recognition model will correctly identify it as such with a high confidence, say 88%. If we add a tiny amount of adversarially chosen noise to this image, we get this image on the right, which we'd all agree is still the same cat. But the model now believes with absolute certainty it's looking at the picture of guacamole. So there's clearly something wrong with our machine learning models here. And the main thesis of my work in this area is that we should approach this problem first and foremost from a computer security perspective. There's essentially 2 main insights that computer security contributes here. The first is about analyzing the threat posed by these adversarial examples in the context of real deployed systems. And that means not just showing that machine learning models in general can be made to misclassify inputs, as we just saw, but to identify settings where machine learning models operate in the presence of real adversaries who have incentive and ability to attack these models. And as I'll show, by doing this threat analysis, we can uncover new ways in which adversarial examples interact with a full deployed system to cause harms that go beyond just mere misclassification. And the second core insight from computer security in the space is about how we should think about evaluating defenses against such adversarial examples. One of the core driving principles from security evaluations is that one should always consider adversaries that tailor their actions to defeat a specific defense. And so I'm first going to talk about my contributions to the threat analysis of adversarial examples, and we'll talk about defense evaluations after that. So the results I'll present here come from a work I did 2 years ago with 2 awesome undergrad students, Pascal and Gilly. What we showed is that adversarial examples are a particularly compelling threat in the context of online content blockers, in particular ad blockers. We found quite surprisingly that using machine learning models in this context could open up new vulnerabilities that threaten a user's web security more broadly. This work had a direct impact, as I said, on AdBlock Plus, an ad blocker you might be using, and this actually led them to abandon some of their envisioned machine learning approaches. So the setting we'll consider here is one you're probably familiar with, where a user wants to browse the web without seeing all the ads that publishers and advertisers want to push onto them. So what many users, including myself, do is that we install an ad blocker, such as AdBlock Plus or Brave, and this is a software that users run locally to detect and block ads. Many of these ad blockers have recently started experimenting with using machine learning techniques from computer vision specifically for this task. So in this scenario, machine learning is clearly faced with adversaries, namely the publishers and the advertisers that have financial incentive to try and modify the website's content to evade automated blocking. And adversarial examples are really the perfect tool for this, because the advertisers want to show ads to users without making any perceptible changes to them, but they want to fool the machine learning model in the process. And our work showed that these ad blockers based on machine learning are actually very easy to evade. So here you can see one of our attacks in action. So on the left, you see a machine learning model trained to detect ads, and actually does a pretty good job. And on the right is the same thing under attack, where the adversary has made tiny changes to the web page content to cause the ad blocker to fail. I mentioned that we'd also see ways in which adversarial examples can cause further harm than just making a model misclassify, which is what's happening here. So let me talk briefly about that. So one of the more ambitious things that AdBlock Plus wanted to do is to run a machine learning model directly over a screenshot of your entire Facebook feed to identify all the ads that you see at once. And what we show is that this would be a disaster for web security, because it essentially ignores security boundaries that are imposed by the application, in this case Facebook, and by the web browser. So for example, we showed an attack where a malicious user, here Jerry, could upload malicious content that would cause AdBlock+'s model to identify content from another user, say from Tom, as an ad. And so if this model had been deployed, you could have seen attacks where users could cause each other's content to be censored by the ad blocker. And so this is a perfect example of a case where considering adversarial examples in the context of a broader system serve to highlight new vulnerabilities and attack vectors. I should also mention here that advertising, which we focused on in this work, is just one example of a broad class of content that people might want to block online, often using machine learning tools. Another interesting case study of this happened about 2 years ago when users were trying to re-upload a live video filmed by a terrorist in New Zealand, and different social media platforms were trying to automatically take this video down. And despite their best efforts, hundreds of thousands of copies of this terror attack video bypassed automated detection because users kept slightly changing the video. And so users were implicitly exploiting adversarial examples in these detectors here. So I've illustrated some of the surprising things that we can do with adversarial examples when we think of their impact as part of a broader security system. So I'm now going to focus on how we should view the evaluation of defenses against adversarial examples through a security lens. And really, the driving principle from empirical security research is that to get a measure of how effective defenses are and to ultimately build better defenses, we should spend a significant fraction of our work on attacks. And these attacks should always be designed explicitly so as to circumvent the specific defense we're evaluating. We call this an adaptive attack. So next, I'm going to be talking about some of my contributions to adaptive evaluations of defenses against adversarial examples. The work I'll talk about here focuses on a recent empirical study that I initiated on the effectiveness of defenses against adversarial examples. So what we did in this work is that we systematically reevaluated 13 defenses that had been published in some of the leading conferences in machine learning over the past 2 years. And what we found is that in all cases, there were serious limitations in how robustness had been initially evaluated. And counterintuitively, we found that existing adaptive evaluations often failed because they were overly complex. And we showed that for each of these defenses, a simpler adaptive attack strategy could break the defense. And one contribution of this work that I'm particularly excited about and that I'll tell you more about is a new adaptive attack strategy that we propose called feature collisions, and which actually draws some inspiration from collision attacks in cryptography. So I'm first going to start by formalizing what we mean by evaluating a model's robustness. It turns out that this is surprisingly tricky. This is one of the reasons why this problem is so challenging. So we're going to consider a standard supervised learning setting here, where a model, which I denote by F, is trained on a distribution of labeled inputs. So say X is some web content and Y is a label indicating whether this content is an ad or not. When the model is deployed, it has to classify inputs that come from the same distribution, say content from new websites. But now there's an adversary that can tamper with the model's inputs by adding some noise to them. And so what kind of noise? That's really the million-dollar question here. So ideally, we'd like our models to be robust against any perturbation that's small enough to maintain the input semantics. But that definition is hard to formalize. And one of the core reasons we want to use machine learning in the first place is because we want the model to learn the input semantics rather than having us formalize them. And so instead, we usually consider a relaxed version of this problem where we limit the adversary to only using a very specific type of noise, say noise that has small Euclidean norm. And we capture this here by some set S of allowed perturbations. We certainly want our models to be robust to such noise, so you can think of this as a necessary condition towards achieving general robustness. But it's not a sufficient condition in that an adversary could also apply other types of small noise. For example, the adversary could shift an image by a few pixels. This is going to be a perturbation that has a very high Euclidean norm, but is still going to be imperceptible. And so while this relaxation of the adversary is somewhat artificial, our hope is that by studying this now well-defined problem, we'll make progress and invent defensive techniques that improve a model's robustness in a more general sense, and not just for perturbations from this chosen set. And ultimately, as with any form of research, we hope that we'll learn something new and exciting along the way, in this case about why machine learning models are so brittle. So given this formal model, we can view the evaluation of robustness as an optimization problem. Given a labeled input, the adversary's goal is to find a worst case allowable perturbation, and we'll define this as the perturbation that minimizes the model's confidence in the correct class so that we get a misclassification. The way that we solve this optimization problem is typically with gradient descent. What you see on this plot is the model's confidence in the cat class for different images. At the center is our original cat image, which has a very high confidence. And as you move away from this image by perturbing it, the model's confidence drops. If you move in a random direction from the starting point, you need to add a lot of noise until the model finally changes its classification. So here, this very noisy image is classified as a lynx. And if instead you always move into the direction that minimizes confidence locally via gradient descent, you actually only need to add a very small amount of noise before you find an adversarial example. So you can think of the process of finding adversarial examples as being a bit like downhill skiing on this confidence mountain. Because we're dealing with deep neural networks here, this optimization problem is not convex. And so in general, we can't hope to solve it exactly. It turns out for most machine learning models, this doesn't really matter. And we can easily find good solutions to this optimization problem with standard gradient descent. The reason is that if we zoom in on the model's output function here, locally, it looks a bit like the picture here on the top, sort of nice and smooth. So perfect for skiing or for gradient descent. And the problem is that many defenses against adversarial examples completely break this smooth structure. And so the optimization landscape now looks a lot more like the picture here on the bottom, with lots of steep spikes that definitely don't make for a nice skiing experience. And this phenomenon is called gradient masking because it basically prevents gradient descent from properly solving our optimization problem. But crucially, notice that this doesn't actually make the model more robust. Adversarial examples still exist at the bottom of the mountain somewhere. It's just going to be harder to find them. What this means is that we have to be very careful when we evaluate robustness. We have to make sure that for each new defense, we'll build an optimization strategy that is specifically tailored to it. So this is what we call an adaptive evaluation or an adaptive attack. And this is really a core principle here that differentiates the evaluation of an adversarial property like robustness from the evaluation of a static property, like say the model's accuracy, where we can just use the same test set for each model. We don't have to adapt to the specific model. So sometimes when we evaluate robustness, standard gradient descent is going to be enough because the function we're optimizing is very smooth. And other times the function isn't smooth at all. So we'll first need to find a way to make it more smooth in order to optimize it. And I'll discuss some techniques to do this later on. And in some extreme cases, defenses are just going to be so erratic that we'll need to stop and restart a bunch of times because we get stuck in a local minima. But the point here is really that we're going to adapt our optimization strategy for each defense that we're evaluating. So let's get back to these 13 defenses that I said we reevaluated. The way that we picked these defenses is that we looked at all published defenses at NeurIPS, ICML, and ICLR of the past 2 years, and chose all the ones that attempted to perform such an adaptive evaluation. And the initial hypothesis we set out to test was whether these evaluations were actually effective or not. So whether the claimed robustness of these defenses really holds against the worst case adversary. And unfortunately, we found that the claimed robustness was consistently overestimated and often significantly. That most of these defenses don't actually improve robustness at all against a strong adaptive adversary. And in our work, we illustrate some of the design patterns we followed to design these stronger attacks. So I'm now going to give an example of how to design a strong attack for a very popular class of defenses, which are those that detect adversarial examples. So such a defense has two components. First, it runs a standard neural network to classify the input. And then it runs a second detector model that collects some internal values computed within the neural network and decides whether the input was perturbed or not. And now if we give the model an adversarial example as input, the classifier might get fooled. But the premise of these defenses is that adversarial examples will leave a very different signature in the network's internal values, and this will be detected and the attack will fail. And this class of detector defenses is very popular because there's a very large variety of possible designs for the detector module using different statistical techniques. And it's very easy to build detectors that successfully detect fixed and known attacks. And so these defenses can often give the illusion of being very effective. So how are such defenses usually evaluated against adaptive attacks? So I'll first show that the standard way of doing this introduces a lot of unnecessary complexity, and I'll then show how to design a simpler and stronger attack. A natural approach here is to set up an optimization problem that balances these two objectives here. So getting the classifier to output the wrong class by minimizing the confidence, and getting the detector to accept the input as valid. And there's nothing wrong in a formal sense with this optimization problem. If we solve it, we'll find an adversarial example if one exists. But this already adds an extra layer of complexity here because we now have to make sure that these objectives are reasonably balanced. And the complexity, unfortunately, doesn't stop here, because many detectors using these defenses are actually hard to optimize over, because they tend to include components that are either stochastic or discontinuous or numerically unstable, just altogether not very well suited for gradient descent. And so typically the attack then has to be augmented with additional complexity to handle these optimization difficulties. So for example, we could take an expectation over the detector's randomness, or we could approximate non-differentiable components with some smooth alternatives. So we now have this complicated optimization objective, and if our optimization fails, it's very hard to figure out if this is due to the defense actually being robust or because of some issue somewhere in the optimization pipeline. So I'm now going to present a new attack called feature collisions, which circumvents all this extra complexity. So the first insight is that we're going to decompose the system into two parts. The first part is going to be the first half of the neural network, which I call the feature extractor. This function computes some internal values at an intermediate layer of the network. The second part of the system, which consists of the rest of the neural network and the detector, these take these features as input. And we're just going to forget about the second part of the system entirely for now and focus only on the feature extractor. The second insight is that we'll target a natural input from a class we'd like to reach, say guacamole. So we'll take an image of guacamole and feed this through the system. And because the system is accurate, it will classify this as guacamole, and this won't trigger the detector. So what we do now is that we look at the internal features that the network computed for this input and save these as our attack target. And we'll now be looking to generate a collision in the feature extractor. So what this means is we're going to search for a perturbation of our cat image that causes the feature extractor to output features that closely resemble the features of the guacamole image. And this optimization problem I'm solving here is now nice and easy to solve because I'm disregarding the detector module entirely, and so we got rid of all of this extra complexity. And when we now feed this adversarial example back into the full system, we're essentially exploiting a garbage in, garbage out type of phenomenon. So because the network's internal values are now the same as those of the guacamole image, the rest of the system can't distinguish this from a guacamole image, and so the attack will succeed and go undetected. And this feature collision attack is actually a very effective adaptive attack for defenses that follow this detector blueprint. There were 4 such defenses among the 13 we studied, and we break each of these with a variant of this attack strategy. So luckily, the situation is better for a number of other defenses. So there's essentially 2 classes of defenses that have emerged over the years that are robust even to adaptive adversaries. One is called adversarial training, and this gives you empirical robustness guarantees. And there's another class of so-called certified defenses that even give you a formal proof of robustness for a given input. So given that these defenses exist, you might ask, well, why are we still trying to find better defenses? Haven't we solved adversarial examples? And unfortunately, not quite, because these defenses don't generalize. So if you recall, when we defined robustness, we made this relaxation where we only allow the adversary to use perturbations from a specific set, say noise of small Euclidean norm. But what all these defenses do is that they're explicitly tailored to this set, and they only end up being robust to the specific type of noise that we chose. And so these defenses come short of our ultimate goal, which was to find ways of making models more robust in a general sense. And my work has actually shown that there are some fundamental barriers here towards making these defenses generalize. For example, these defenses overfit to the chosen set of perturbations, and extending them to richer sets hurts the model's overall robustness. So I won't get into the details of these results here, but I'm very happy to discuss them more after the talk if you're interested. So the takeaway here is that unfortunately, we don't yet have machine learning that is robust against adversarial inputs. There's a somewhat sobering message here that despite tremendous progress in machine learning over the past decade, some security-sensitive applications, like robustly blocking ads, for instance, are still out of reach. My work has helped raise awareness of this fact in industry, for example, in the ad blocking space, and this has helped prevent the deployment of some insecure systems. And within academia, my work has also helped spearhead the adoption of more principled evaluations of robustness. And we're really seeing a positive trend of defense evaluations becoming more rigorous and principled. And I think that taking this more principled, security-minded approach will be the way forward to ultimately solving this extremely challenging problem. So looking forward, I think that this work on attacking machine learning is also going to become very relevant beyond settings where there's an explicit adversary. These attacks are going to be useful as a general way to create worst case test scenarios for safety critical systems that achieve a very high average case reliability. So to illustrate this point, 2 years ago, we showed that computer vision models could be made to hallucinate a stop sign on a concrete wall. And here, I don't really see this as a particularly concerning attack vector, in that if someone actually wanted to crash my car, there's probably easier things for them to do, like they could throw rocks at it or something. Instead, I think that here these adversarial examples can be great worst case tests that can help us to understand how the system as a whole should be designed so as to be resilient to occasional failures in the machine learning models. So this concludes the first part of my talk on using adversarial examples to evade machine learning. So we're now going to switch gears and talk about protecting the privacy of users of machine learning systems. And as we'll see here, things will look a lot better because we do actually have the right formal foundations for reasoning about privacy. What I'm going to show here is how to use decade-old techniques from machine learning to make our models more private. So machine learning models are often trained by combining private data from many users, say their text messages to train a smart keyboard. Of course, in practice, this means that we end up sharing all our private data with some large company like Google or Facebook, and this is bad for our privacy. But what I'm going to focus on here is maybe even a deeper issue, which is that the machine learning model itself can leak part of its training data once it's deployed. And so the threat now isn't just that, say, Google sees your text messages, but that potentially any user gets to see them. And this threat is unfortunately quite realistic. So in a very recent work, we showed that generative text models like OpenAI's GPT-2 model can output some of their training data, even if this data only appeared once in the model's training set. So in one particularly compelling example showed here, we got the model to output the exact contact information of an individual, his name, email address, phone, and fax numbers, which are redacted here for privacy. And such a data leak can, of course, be disastrous for users whose private data gets leaked. So this could lead to identity theft, harassment, and so on. And regulations such as the GDPR are also starting to crack down hard on companies that endanger user privacy in this way, with sanctions that could be huge fines, of course. But there's even been a recent case in the US of a company being asked to delete all machine learning models it had trained because it had violated its users' privacy policy. So now I'm going to show how to train models that provably prevent such data leakage using the statistical notion of differential privacy. An interesting technical contribution here is that I'll show how to obtain better private models by not following the usual approach of trying to make deep learning models private, but by instead resorting to some decade-old feature engineering techniques. So let's first talk about differential privacy, which is actually the perfect formalism for capturing our goal here of training models that don't leak their training data. So differential privacy does is that it enforces that if we train on any two data sets that only differ in a single element, we'll obtain any given model as output with roughly the same probability. And so the training algorithm can't overfit or leak any individual data point. The level of privacy that we achieve is governed by this parameter epsilon here on the right, with lower values of epsilon corresponding to more privacy. And the way we train models to be differentially private just requires a small change to how we normally train machine learning models with gradient descent. So to make gradient descent private, what we do is we add noise to each of the gradients. And by increasing the amount of noise, we'll get a better differential privacy guarantee, but will also hurt the accuracy of our final model. So there's a trade-off here. So how well does this work? So let's first talk about non-private learning, so we have a baseline to compare against. I'll focus here on the CIFAR-10 benchmark. It's a very standard benchmark in computer vision that consists in classifying small images from 10 different classes, 5 of which are shown here. And over the years, especially since the explosion of deep learning, we've gotten to near perfect accuracy on this task. We can now get over 99% accuracy. Once we add differential privacy to deep learning, things look a lot more bleak. So here for a privacy budget of epsilon equal to 3, there's a roughly 40% accuracy drop between the best non-private deep learning model and the best private one. And this drop essentially reverses a decade of progress on this benchmark and brings us back to accuracy levels from before deep learning. And so what my work shows is that you can improve private learning exactly by not using deep learning. So specifically, I take some of the techniques that performed well 10 years ago and show that those can be made private with only a small drop in accuracy. And overall, we perform better this way than if we used private deep learning. So how did we used to do machine learning, and more specifically computer vision, 10 years ago? Well, instead of training a deep machine learning model directly on images, we would first extract some special features from images, and then train a rather simple classifier, say a logistic regression, on top of these features. Importantly, these features were not learned. Rather, they were engineered mathematically to capture some prior about the data domain. Say that important image features should be invariant under rotations or scalings. And the important point is that extracting these features, which we call handcrafted features, this doesn't affect privacy because this can be done independently to each image in the training set. And then we're just left with the task of training a simple classifier with differential privacy. And training a private classifier on top of these handcrafted features works much better than doing private deep learning from scratch. So on this graph, I show the accuracy that can be achieved with either technique as a function of the privacy parameter epsilon. And remember that smaller epsilon corresponds to better privacy, and this tends to hurt accuracy. But the approach with handcrafted features is consistently better. So why is that? So essentially, there's a trade-off here between how expressive the classifier's features are and how easy it is to learn a near optimal classifier. So let me explain what I mean by this. So when we learn a model directly in input space, so directly over raw images, we know that we can train classifiers that reach nearly 100% accuracy. So as I said, we can reach over 99% accuracy on this task. But these classifiers are very complex, and it takes many steps of gradient descent to learn them, and that's bad for privacy. And when we look at handcrafted features, the situation is essentially reversed. So you can think of the feature extractor as blowing up the inputs into a higher dimensional space, but this feature mapping isn't perfect, and this actually hurts accuracy. So the best accuracy you can reach in feature space is typically going to be lower, say only about 80% accuracy. But critically, reaching this accuracy is going to be possible even with a very simple classifier. And so we can learn this very efficiently and at a low cost in privacy. From this, it seems that if we wanted to do even better than with these handcrafted features, we'd need privacy-free features that are more expressive, that would somehow allow us to train more accurate classifiers. One way to do that is to learn good features. And since we want to do this in a way that preserves privacy, we're going to learn these features on a different data set that is public. In machine learning, we call this transfer learning. So what we do here is we first train a deep neural network on a public data set, which isn't privacy sensitive, say the ImageNet data set. And then we use this model as a fixed feature extractor that we can apply to our private data set. And then again, all that's left to do is to train a simpler classifier, say a linear classifier with differential privacy. And private transfer learning is actually incredibly effective, in that if we have access to a large public data set like ImageNet, we show that we can privately train a model on CIFAR-10 to near perfect accuracy. And this result was actually quite surprising because even though transfer learning is a fairly basic technique in machine learning, prior work in this space, which mainly came from large industry labs, had never really tried to perfect this approach. And the reason seems to be that these companies had mainly focused on settings where there's a very large amount of private data available, as those companies indeed have access to usually. But for settings where data is harder to get, like in medical settings, for instance, I think that my work here really shows the right way of doing private learning, which is to first find good public features for your task, either handcrafted features or features transferred from a public data set, and to then just fine-tune a much simpler private classifier. And this consistently performs much, much better than private deep learning. So differentially private learning is a very hot topic in industry right now. And in the process of doing this research, I used and contributed to some of the leading open source projects in this space to make it easier for others to replicate my results and to build upon them, which I encourage you to do if you're interested in this topic. So as part of this work, I refactored part of Facebook's differential privacy library to enable some critical performance improvements that are now part of their main tool. And my work also surfaced some mistakes in the privacy analysis of the libraries developed by Google and IBM, which are in the process of or have now been fixed. So now that we've seen how to train machine learning models to preserve the privacy of the training data, I'm going to briefly talk about threats to privacy for the users of these models once they're deployed. And here I'm going to show how some of my work combines ideas from cryptography and machine learning. So we'll consider here the problem of deploying a machine learning model to the cloud in a sensitive setting such as healthcare. The reason you might want to do this is to benefit from the cloud's better performance and reliability, especially since cloud providers often invest heavily in hardware that's tailored to serve machine learning models. The problem is that even if the model was trained in a privacy-preserving way, say with differential privacy, users still have to upload their data to the cloud in order to use the model. And so the cloud provider just sees everyone's sensitive data. So to solve this problem, I designed Slalom, which is a system that enables users to securely use machine learning models in the cloud, even if they don't trust the cloud provider. So Slalom's design goals are to achieve the standard cryptographic notions of confidentiality and integrity, in that we require that a malicious cloud provider can't see the user's test data and that they can't tamper with the model's outputs. Note here that this confidentiality guarantee is very different from differential privacy. So differential privacy asks that the model doesn't leak any of its training data. And here we're asking that the party that hosts the model doesn't get to see any of the data that users send to it. And Slalom achieves these goals by combining ideas from very different fields, namely from machine learning systems, hardware security, and cryptography. And a key feature of Slalom, as we'll see, is that it is designed to maximally make use of the cloud's special purpose machine learning hardware. So we'll first consider a baseline solution that Slalom builds on, which consists in running the neural network in a so-called hardware enclave. So how this works is that the user encrypts their data, sends it to the cloud, and the cloud's hardware will decrypt the data in a special protected memory region called an enclave. The enclave runs the model, re-encrypts the output, and all of this happens without the cloud provider being able to observe or tamper with the computation. And so we get confidentiality and integrity. And such hardware enclaves now exist on many commercial and academic processors. And I have to note here that the security of these enclaves has been called into question by some recent attacks, but let's assume for now that we have a secure hardware enclave at our disposal. The other issue here is that these enclaves currently only exist for relatively low-end general-purpose CPUs. And so any special-purpose hardware that the cloud invested in, say GPUs or TPUs, can't be used because they don't offer any of these hardware security guarantees. And so to solve this problem, Slalom introduces a special cryptographic protocol that lets you leverage untrusted special-purpose hardware without sacrificing confidentiality and integrity. The way this works is that the slow hardware enclave is going to outsource most of the work of evaluating the model to, say, a GPU. but it's going to use cryptography to preserve both confidentiality and integrity. So let me give a few technical details on what Slalom actually does. So at its core, Slalom is a protocol for outsourcing matrix multiplications or convolutions, and these form the bottleneck of neural network evaluations. The problem is that if we just ask the GPU to perform a matrix multiplication between a user's input X and a model weights W, we'll get no confidentiality because we're just sending the user's inputs to the GPU. So here's where we use cryptography. First, we're going to represent all the values that we compute with as integers modulo a large prime. And then we can mask the input sent to the GPU with random values. And so this provably gives us confidentiality. And since matrix multiplication is linear, we can later unmask the results using values that can be pre-computed ahead of time because they don't depend on any user inputs. I should note here also that in practice, we're actually going to perform all these integer computations using floating point arithmetic. And so we don't actually have to make any changes to how the GPU operates or how it computes matrix products or convolutions. The remaining issue here is that we still have no guarantee of integrity. Namely, a malicious cloud host could just return garbage data every time we outsource a matrix multiplication. And so the final step in Slalom is that we'll use a fast probabilistic algorithm to verify the result of each matrix multiplication or convolution. And here we use this classical result from randomized algorithms that says that you can verify a matrix product much faster than the time it takes to compute it. And so overall, we prove that this protocol satisfies both confidentiality and integrity, even though most of the heavy work is now done outside the enclave. By being able to leverage special purpose hardware, Slalom achieves much better performance than our baseline, which was to execute the entire model in the hardware enclave. The performance metric we consider here is inference throughput, so how many images per second can our system classify? And Slalom improves throughput by up to an order of magnitude for large models like VGG16, and by at least a factor 4x for smaller models like MobileNet. Okay, so this concludes what I wanted to present about some of my past work on machine learning security and privacy. So let me give now some thoughts on where I think the future work in this space could go. Machine learning security and privacy are going to be one of the critical challenges for our society in the future, because machine learning is set to play an ever more central role in some critical infrastructure and in decision-making, such as in credit scoring, criminal sentencing, or hiring. And if such systems are going to be deployed, we really need them to be trustworthy. A holistic term I'm using here that covers not only robustness, but also properties such as fairness and interpretability. And the challenge is that all of these properties are very hard to formalize. And as we saw with robustness, this makes it a challenge to evaluate models and to build better models. My hope is that we'll be able to emulate what was done for data privacy with differential privacy. In that before differential privacy, we also didn't really know how to formalize what was meant by privacy. And so things kept getting broken left and right, a bit like with robustness today. And so I think that we also need to come up with better definitions for properties of trustworthy machine learning in order to make progress in this space. I also think there's much more to do at the intersection of cryptography and machine learning. My work on Slalom was one example of how to leverage cryptography to improve the privacy of machine learning systems at deployment. But for other properties I've talked about, like robustness to adversarial examples or for differential privacy, we always here implicitly assume that the adversary was computationally unbounded. And so there's an interesting open research problem here on whether we can build models that are not necessarily unconditionally robust or private, but where attacks are provably very costly. As I mentioned earlier in the talk, I also think that techniques from adversarial machine learning are going to increasingly be necessary to evaluate machine learning in areas where models have to be highly reliable, say in healthcare or self-driving. Basically, some of these applications are not going to be given the green light for deployment until they hit a very low error rate, say a 1 in 100,000 or 1 in a million failure rate, as we'd expect in other engineering disciplines. But at that point, our standard way of evaluating machine learning models by computing accuracy on a held out test set it's just not going to be particularly relevant anymore because we need a huge test set to just find a single mistake. And so instead, what we'll want to do is to probe these models adversarially to better understand the few ways in which they still fail and can be improved. So with this, I'll conclude my talk by reiterating that machine learning is currently hard to trust, given its lack of robustness and privacy. There's really hope here that we can do much better than with current machine learning. When it comes to robustness, we as humans seem to be proof that robust prediction is possible. And I strongly believe that to make progress in this area, we have to approach it with a computer security mindset. And for privacy too, we can do better than what we're currently doing. And the tools for doing this, fortunately, already exist. For example, I've shown that we can train models with differential privacy or deploy models with hardware protections and cryptography to better safeguard users' privacy. Thank you. That's it.